Hi there. In this lecture, we are going to explain what a union of two events is and how we can use it. Okay, now we know which part of the graph represents the intersection of A and B. But what if we only require one of them to occur, regardless which one? That is the same as asking either A or B to happen. In such cases, we need to find the union of A and B. The union of two sets is a combination of all outcomes preferred for either A or B. If you think about different American states as separate sets, then the citizens of each state would be their elements. Just like every Texan is an American, so is every element of an individual set also an element of the union. We denote the union of two sets as A union B. The symbol we use is just the intersection symbol flipped upside down. To avoid confusion between the two, remember the symbol for union resembles a capital letter U. Okay, let us examine what the unions would be in the three different cases. If the sets A and B do not touch at all, then their intersection would be the empty set. Therefore, their union would simply be their sum. Intuitively, this makes sense. No element is in both sets simultaneously, so we do not need to worry about double counting. Going back to the card example, the union of hearts and diamonds would be all red cards. No card can have multiple suits, so we need not worry about counting a card twice. Therefore, the number of red cards equal the union of cards, which are either diamonds or hearts. If the events intersect, the area of the union is represented by the sum of the two sets minus their intersection. That is because if we simply add up the area of the two sets, we would be double counting every element that is part of the intersection. For instance, 5 people in the office have blonde hair, 4 people have blue eyes, and only Kate has both. Therefore, there are only 3 non-blonde people with blue eyes and 4 blonde people with non-blue eyes. Thus, the union of blonde and blue-eyed colleagues is the sum of people who have precisely one of the two features, as well as Kate, who has both. Mathematically, this result is 3 plus 4 plus 1, or 8 employees satisfying at least one of the conditions. Alternatively, we can compute the union using the formula we mentioned earlier. We have 5 blondes plus 4 blue-eyed people minus 1, or a total of 8 colleagues who possess at least one of the two distinct features. In this instance, the minus 1 represents Kate, who is the intersection, since she is both blonde and blue-eyed. We can use the notation we learned so far in this course to express this. The union of A and B equals the sum of the sets of A and B minus their intersection. In fact, the union formula we just showed you is universally true, regardless of the relationship between A and B. Okay, so what happens if B is a subset of A? Well, in that case, the union would simply be the entire set A. Imagine event A is being from the US, and event B is being from California. If you talk about all the people who are either from California or the United States, you are simply talking about all the people from the USA. Remember that the intersection of these two sets is equal to the entire set B, so the intersection of A and B represents all the people from California. If we plug this into the formula from a few minutes ago, that would give us the following statement. The union of all people from California or the United States is the sum of all California natives and all Americans minus anybody born in the Golden State. After canceling out all Californians, we get exactly what we expect. The union of people from either California or the United States equals the entire population of the USA. Now that we know what unions and intersections are, we can talk about mutually exclusive sets. In the next lecture, we are going to define the term mutually exclusive and discuss certain characteristics of such sets. Thanks for watching.